Thanks again for making it out of the presentation. The topic for today's presentation is I'll be presenting on some of the work I've done on a state estimation-based approach to cybersecurity in grids that have AC and DC components. And the work's in collaboration with Al Valdez and Richard McQuan at ITI in conjunction with folks at ABB Research. So here's a rough outline of my presentation, provide an introduction and a motivation as to why we're going about what we're doing, the particular class of threats that we look at, what is the approach that we're proposing exactly, and sort of a somewhat heuristic detection criteria. What are the main features for the approach to be effective? Give you a basic layout of the study, so apply this method in one specific use case and see what kind of results we get. And I'll present on the results of that, and we'll be able to draw some conclusions on how effective this approach that we're proposing actually is. So what's the problem? So the problem is that now, as we're getting very familiar with the fact that power system operation and control is increasingly happening over cyber physical layers. So the grid of today has more and more cyber physical components. So not only do they interact over copper, traditional copper wired communication, but a lot more of digital communication. And so with this flourishing of additional devices in the system that can be accessed over a network, the possibility also is increasing that potential threat perpetrators can gain access to these cyber physical layers and then compromise the system's ability to function correctly. So how is it addressed these days? Well, one conventional approach that is utilized, which is sort of an IT software-based idea, is, well, you look at the messages that are coming and going, and you try to make sure that the messages are coming from the source that you believe they should be coming from, and you observe sort of the message syntax. So if it's some kind of communication protocol like DNP, then you observe the message envelopes to make sure that they're syntactically correct. So, but if we are system operators, or if we have some deep understanding of the system, well, then maybe we can use that knowledge to our advantage in some complementary sort of way. Maybe we can use that for a detection method. And that's what we're really approaching over here. It's a power systems-based approach to this threat detection scenario. And the threat that we'll consider are what are essentially called data integrity attacks. So when you send data over some kind of communication channel, the person on the other end may not know what is being sent. If they did, then there was no possibility of a threat happening in the first place. So the person may not know what's the thing that's being received at the other end is true when compared to what was being sent. So these are the data integrity threats. And one thing that they are sort of characterized by is that they're syntactically correct, which means that they've somehow been able to bypass the IT-based features for detection. And so it would be, imagine a control signal that's sent out to a power system. That signal has been corrupted in a way that you could not detect it through some error examination of the message syntax. And if that gets implemented, well, then your system will respond in a way that you do not want it to. So what is the basic thrust of the approach? Well, the approach is pretty straightforward. It's, so to speak, perform a consistency check. If you know what you're sending out, so you have an understanding of the system, then you have an understanding of what the system should respond like. And so if you know what you send, and if you keep observing the system as it implements that control command, then that observation should match closely with what you expect it to do. Hence the idea of this consistency check. So imagine some control action U of t a very general sort of idea that's being implemented over some period of time. And say you had is the system's observed behavior that you compute in any sort of way. And in that same time interval, then you expect that the control action you've sent and then the control action that's being implemented should match reasonably well, accounting for all sorts of errors that you might have. So the system's observed behavior, what we're referring to here, is something that we can infer by state estimation. Hence the state estimation based approach that's being proposed here. And a very reasonable way to say, well, how do we quantify this variation? Well, you can say, this minus that if it goes past some error threshold or something, and you say, okay, I'm not willing to tolerate a change more than that. We're doing something very similar here. We're saying that the accumulation of the errors, so these lowercase u's are essentially time derivatives of these functions. So how is that control command changing the system's behavior? If that is far too deviant from what is expected in time, and you're accumulating all these errors, then after a while you can say, no, these errors have gone on too much. They're accumulating at too fast a rate. So we'll say the moment this error function goes past some desired or set error, a threshold, then I'll say, okay, no, I'll flag that time. I'm saying there's something wrong that happened at that time period. I think there's been a compromised execution.
So a command need not be continuous.
Yes.
So that, what you said, those are the derivatives may not exist.
That is correct. And this would be, I'll draw some, in the conclusions, we'll essentially say that there would be, the control commands that would be restricted to looking at would be something that changes in some well-defined fashion over a reasonably long period of time. So something that's not instantaneous. So for the approach to be effective, what becomes important here is that to make sure that we do this consistency check at a very sort of fine level. Do it as soon, as frequently as possible. But to do that, which means that we have to observe the system's behavior with a high time resolution as well. And so for a large power system, it means computing state estimation very, very frequently. And that can be a problem. State estimation is an overdetermined problem, but it requires lots of measurements to come in and have that much data available to perform that computation at every time. So to be able to do that computation at every frequent time instant, we make two certain approximations here. One of them is you say, well, I'm only going to choose a very small set of measurements to receive at any time. If a system has 5,000 buses, the number of states I'm trying to estimate is like 10,000 approximately, which means I need at least as many measurements, probably more. So I'm saying, no, we'll take a very small set of measurements that we'll focus on, and then we'll supplement them with these other bits of information that will help us keep solving that problem. And the other thing we'll do is we'll reduce the number of iterations in the state estimation computation. So it's a weighted least square problem, state estimation, and it requires an iterative approach when you're using a non-linear model for the system. And so we say, well, we don't necessarily need to compute it until we get to some solution. If we stop it after a few iterates and we see a solution that's reasonably good, we take it. So that's essentially the general idea behind the approach. That's the general thrust. And here I'll talk a little bit about what the specific thread that we're going to look at and the case study that we're going to look at. So the case study is looking at a thread that's directed on a high voltage DC line in a large power combined AC-DC system. And so the specific case, to add some sort of realism into the case that we're using is this synthetic network developed for the WEC system, so the Western US Interconnect, and in which we model this Pacific DC intertie. So the system size that we're working with is approximately 2,500 buses, 5,700 lines. And we'll be looking at the power order command that's sent on this line. And we'll see how effective is the approach in tracking this power order. So how does this work in a sort of real case so that we can appreciate how this goes about? The power flow on the HVDC line is usually determined by some kind of optimal power flow solution. So if there is a demand at the other end, then the sending end will send that power over. So HVDC links are often used in networks to help ease congestion because you can very accurately control the flow on those lines. And the way it works with the Pacific DC intertie actually is that the dispatch signal, so the power that's supposed to go on the line, is communicated to the converter stations at either ends via a telecommunication link. And then the power order is then executed at those DC stations locally. So there is an operator that sits there who receives this information and then acts upon it. So all controls are local. So the major threat to this is the major threat to this HVDC line is then when someone can alter the power order command that was sent for dispatch. So if the system operator says, I want 200 megahertz flowing on the line, that signal can then, while being transmitted, can be corrupted to say 500. The person on the other end has no idea what is the actual solution. He or she is going to take that at face value and implement it. And in an attempt to additionally sort of hide their corruption of this order, it is not uncommon for an adversary to spoof measurements that are going to be received from that HVDC center as well. So essentially that entire subblock in your system is now suspicious. You cannot really trust anything in there. So here's a sort of graphical depiction of this threat. You have, your AC network from one region to another. You have an HVDC link. The operator's control center is sending some power order dispatch with an intention of the power flow going from some P0 to P1. That gets intercepted and modified so that what ends up getting implemented on the line is some P0 to P2. And for argument's sake, we can say P2 is greater than P1, but the idea is still the same, even if they're different, even if P2 is actually lower. So what are some of the premises that we're making for this study? Essentially is that the attacker is going to be able to attack the telecommunication link between the control center and the converter stations. But he or she does not have enough information to be able to compromise measurements from the large AC system. And during the time when this power order is executed, the network topology doesn't change. And the system is considered to be in sort of quasi-steady state. So we're not working with any dynamic considerations. So a little bit about the simulation methodology, how we're emulating this approach in software. The case that I showed to you, the web case, is implemented in PowerWorld. And the PowerWorld power flow solver can solve for line flows on an HVDC line across different values of current on the line. So all of those then serve as data, incoming measurements from the system to some computational platform. And our computational platform is MATLAB. So there's a state estimation computation that's being done on MATLAB. And so every time we compute a state estimate, we use that estimate to compute an estimate of the power injection on the ends of the line. So we essentially know, okay, if I ask for 1,000 megawatts being withdrawn from the line, well then, at no point in time should that injection significantly be different from 1,000 megawatts. So I talked about the prioritization metric, that we'll choose a very small subset of lines to receive measurements from. And how do we do that? Well, here we're justifying them through the use of the power transfer distribution factor, the PTDF. And what the PTDF essentially is it's a fractional change on a line on the active power flow on a line as some injection occurs in some point in the network and that power is then extracted from some other point in the network. So think of it as a resistor divider, but we're talking about power instead of current. So in any sort of power transaction in a system, very few lines, comparatively very few lines, will bear most of the burden of that power transfer process, and most of the lines in the network will be very minimally affected. So here's an example for our case. And by the way, I should mention, so the PTDFs are signed quantities between -1 and 1, but we are sort of expressing them in percentage, and we're talking about the magnitude of the PTDF. So a 0.5 minus or plus would be a 50% PTDF here. So if you consider in this system with 2,500 buses, 5,700 lines, if I restrict myself to just looking at lines that have a PTDF value of over 5, there's only about 135 lines in that system that I need to consider. If I choose 15, I only have to worry about 28 lines. So those 15 lines, or the 28 lines, contribute a major portion of the line flows, of the power transaction in that system. And so this is what we choose for our prioritization metric. And so remember I mentioned about how state estimation is overdetermined, requires more measurements than the states you want to estimate. So how do we make do while we have to estimate so many states given so few measurements? Well, we use essentially this recursive idea where at any time when we have an estimate, we receive the prioritized measurements. So I'll show this on this block over here. So at any instant in time, we receive the set of prioritized measurements, which are small. But given that I had an estimate for my state at some previous time, I can use that to compute measurements for the other lines in the system. So I can have an estimate on what the flows on the other lines would be in the system. And so I use the previous estimate, come up with these numbers, and then I plug them in. And then so in any real-time instant, I'm taking only a small set of new information from the real system. So how well does this perform? So here I have on the chart here, so this is considering the receiving end of the HVDC line. So the Pacific DC intertie goes from 0 to rated capacity, which is 3,100 megawatts, in about 20 minutes. And so I'm simulating this power ramp over here, and I'm interested in seeing how well this estimation, the approximate estimation, works for me. If I use only 20, how much was it? So I'm using a PTDF of 15% here. So that means I'm considering only 28 lines. 28 lines to receive measurements from. And so here you see so that the circle marks are the power flow results, and the X is the injection estimate I get from that. And this is the error between the power flow result and the injection estimate. You can see it's in a very tight boundary. We've been able to bound it quite well. And if you look at it, this is another interesting thing to note. This injection error is the power flow result minus the injection estimate, and it's sort of positive in this ramp up. And if you think about it, you can kind of gain the insight from here that at any single point in time, I receive measurements from that instant in time, but then I supplement them with some measurements from a previous instant in time. So this state that I'd compute is sort of somewhere in the middle. So hence the error having some non-zero, or in this case, some positive value. We're always lagging what the value should be. And how does the error function look like when we work with this error? So here's the error. And then if you integrate it over time, as time progresses, you get an error function, something like that. So over a full ramp in the system, you can expect your error function to be bounded about by 50 megawatts. So that's some kind of measure of tolerance that we can expect for a value of prioritized measurements of 28 lines. And 5 iterates, by the way, just this part here. Each of these estimates was computed in 5 iterates. And so how does this vary? So we'd be interested to see, well, what is my trade-off in how many lines should I consider versus what is the potential cost of doing it if it were to be implemented at some point. So we look at some sensitivities involved here with the estimate errors as the number of lines being considered changes. So you see over here that at the PDDF of 15 and 20%, I'm still able to have reasonable control over the errors. At 10 and 15%. At 20%, the bound starts to grow. And at 25 and 30%, the bound grows even faster. So depending on what kind of error I'm willing to tolerate, we can make a judicious choice on the number of lines that we decide to prioritize. And then, how does the estimate itself change as my limit on the maximum iterations in the state estimation process changes? So you can see at one iterate, you sort of end up somewhere, but then it's hard to justify using just one iterate sometimes, because it has some unusual performance on one side or the other. It sort of crosses the error at some point and keeps growing. But for the subsequent ones, if you look 2, 3, 4, 5, they all converge pretty quickly. So what it shows here is that our estimates are not as sensitive. The error is not as sensitive to how many iterations I go on for as it is to the number of lines I get. And so how does it look like if we vary both of them together? So kind of gives you an idea in this elementary bar chart. So we have the number of iterations growing here, and then the PDDF threshold growing this way. So more time spent in computation and fewer measurements being received in real time. And the bar is essentially a mean value of the error across all the instants in time at which the estimate is computed. So you can see here that the change to this mean value as you change your iterations is not very high. But as you reduce the amount of new information you get every time, this error starts to grow. So knowing how we can bound this, so the choice of how many lines you want to use to, prioritize at any time, how many iterates you want to stop at, is a matter of heuristics, right? It depends largely on the case that you're studying. But even then, let's see how the estimator actually performs when you have a simulated thread here. So what we're doing here is, imagine this transmission line originally has a dispatch of 1,000 megawatts. So 1,000 megawatts is being extracted from the other end. And then a dispatch order is sent that says increase it to 2,000 megawatts. However, that dispatch is then corrupted to a value of 2,500 megawatts. So this blue trace is what I have sent. And then I see the orange trace is what my estimation in the system is telling me. So the power order is set to execute at this point here, and it should conclude by about this point in time. But as we pass that time, our estimates coming in from the computation platform, it could be an energy management system or something, is saying, well, the estimate keeps growing and then flattens out. So what happens to the error function in this case? So you have this thread simulation that's happening, and your error function, it's going along reasonably well, staying low, and then all of a sudden it starts to increase. So if you decide on a threshold for your error, then you can collate the time at which that happens, and say, well, okay, I was able to detect it in 15 seconds, in 30 seconds, however long, depending on your error function and depending on your desired level of risk, I guess, in one way, you can choose what you'll end up getting a time that corresponds to how much time passes until I detect that threat. So what does it tell us essentially? So what we've presented, the idea is pretty simple. It's doing a consistency check. If you know what you are sending and then the system is implementing it, well then over that period of time, the observation of the system should correspond closely to what you had expected. If it does not, if it deviates too significantly, then you know you have a problem. It could have been either incorrectly received or incorrectly implemented. We do not know what, but it has been, the net result is that it's not behaving the way you expect it to. And so what does the approach essentially end up doing for us? It bounds the extent to which an attacker can compromise something and still evade detection. But again, based on our judicious choices of the lines that we choose to prioritize at any given time, we have control over this bound. So if we can keep this bound small, if we can keep it pretty tight, then this order could be corrupted and detection could be evaded, but it's unlikely to have a very significant impact on the system. So that concludes my presentation. I'll take any questions.
For the iterations, we saw that it's not sensitive towards for greater than one. It's not really sensitive. So what's the reason why you chose 5 iterations for?
So it's sort of a heuristic argument.
Okay.
So you can really change it up as well. And some more extended results that we were looking at, there were some instance in time when it took a little more than 4 iterations or 5 iterations to converge. So largely all of them converged in under 5 iterations, but there were some that took up to about 5 or 6.
Okay.
So just sort of using that as a guide to an upper limit.
Okay.
And each computation here, the time spent per iteration for this large system is about 1/10 of a second. So you have, depending on how quickly you choose to receive measurements in the system, you have some flexibility with this, so that this can be stretched.
Yeah. One more question. If you go to slide 5.
These are not numbers, so I don't know which number
I
5
think
is.
it's all the way to the beginning. Yeah. Well, okay. So, what's the difference between the UT? It says it's being implemented, right?
Mm-hmm.
Difference between implemented, observed, and sent. So observed. Okay. Difference between implemented and sent.
That's good. So in the case when the order is not corrupted, right, sent is the same thing that's implemented. So the implementation is what the operator at the station does.
Okay.
Sent is what I want him to do.
Okay.
Right? So if that order is not corrupted, those things match.
Okay.
When it's corrupted, however, those are not the same.
Okay.
And my observation is not looking at what he did directly, but inferring what he did based on my estimation.
So when it's corrupted, you look at the implementation versus the observation.
You're always looking at the implementation. By this observation. The implementation is, you look at the implementation by this observation.
Okay.
Right?
Yeah, so you assumed a very strong threat model that they're going to be able to compromise this communications channel between the control center and the first end of the HVDC line. And you also mentioned that they can and often do attacks with the measurements as well. So what makes you feel like you could trust the measurements when you got down to 0.6? Would an attacker with that strong with that model
That's a
be able
great
to
question.
compromise
Yeah.
a few measurements?
Yeah, so that's a great question. And so a couple of things. So one thing that this approach can sort of help inform a transmission operator's judgment is the lines or the set of measurements that they may choose to harden the communication on. So that gives them, essentially that gives them the ability to compute these estimates and have a greater trustworthiness in each of these estimates. Additionally, we didn't implement it here, but some strong normalized residual-based techniques for bad data detection and state estimation can also be used. And what ends up happening is that a lot of the false data threats that people look at is in the context of the DC state estimation model. And so you try to inject into the null space of that matrix. What happens is that with a nonlinear model, so the DC estimate is great and it's useful for PMUs and stuff, but the problem is that when you have measurements that are of a different type, say like reactive power measurements or even line flow measurements actually, the DC estimator falls short. You cannot compute the state estimates based just with that model. You have to go nonlinear. So trying to inject into the null space of that can become very hard because that is not dependent on the system's operating point. Good question.
So in this particular film that you studied, you knew exactly where you expected the data compromise and where you expected the mismatch to occur.
Mm-hmm.
How would you extend this approach to a system where you don't know what value the attacker is trying to compromise?
That's a good one actually, and really, so the idea behind this was you have a target that you wish to receive or achieve at some point in the network, and so you implement towards that target, and during the implementation you observe to see if that target is reached. So this sort of presumes that you already have something that you are looking at.
So
It's
safe,
direct.
but it's also kind of dynamic.
Yes,
You're
yes.
trying to get the system from point A to point B.
Exactly. It's like a slow scale dynamic to the point that the fast transients you could choose to not consider and still be fine.
So this method may not detect, for example, instead of the attacker compromising a command sent, just sending their own out of the blue. Because you wouldn't know to be looking for that.
Yes, that's true. In cases like that, however, you could, because you would be looking at the system state regardless over time as well. So that's one of the things that any EMS would be doing. And that could potentially be flagged in an operator's dispatch center.
It's just you don't expect change.
Yeah, it's a very sudden change in something, then that will set off a flag regardless.
So if the attacker were to send a power demand that were within the error, is there any data that shows how that will damage the system if they overload it by a short amount?
That's a good question, and I'm not sure I know the answer to that. Oftentimes what can happen is that, if you have an error of, say, in this case, I think the error was about 50 megawatts. So this was modeled for the Pacific intertie, and the receiving side is actually pretty much the city of LA. So it's a fairly large area that's going to be consuming that power. So they might have issues with ramp down, ramp up capability. So they see an excess amount of power coming in. So the AGCs in that region will reduce power at the generator end. So essentially, like the distributed slack will absorb that power, right? But yeah, that's what would have to happen. So you'd have to sort of know what the limits on your ramping capabilities are in the system.
Do you know what the performance overhead is from doing these computations more frequently, like the faster? I mean, I guess the question is it an overhead or does the reduced time that it takes to compute it make it
So what it
It
helps.
gets faster than you
Right.
normally do.
Well, yes, that's pretty much exactly what happens, is that you essentially, the spacing between the points grows. So if this point jumped to here, but it took a while until you could compute that next one. So this is the amount of time that you would at least have to wait to know whether it has grown past that point. And without exactly knowing the direction in which it's going, it's also very difficult to extrapolate where it's going.
So, are there any kinds of faults that could occur in the system that would show up and look that your approach could get confused with an attacker or anything?
Faults. That's a good question. I do not know if yes, there could be some issues, but the issue would be more concerned with loss of data. So what happens is here, sort of, one of the assumptions that we made, right, was that the system topology doesn't change. So the Pacific DC intertie goes from 0 to 3100 in about 20 minutes typically. It can ramp even faster. It can ramp in about 1,000 megawatts a minute, which is really fast. But so in that time, we are assuming that the topology doesn't change. So we have a very set number of set lines that we're always receiving measurements from.
Mm-hmm.
So if you have, say, your biggest line, so let's say whatever the line is for which the PTDF is very large, that one trips out. So you could have a redistribution, you'll have a redistribution in this PTDFs. So that would be something that a fault will cause. And that can screw up your results to some extent, because you might actually be pushing your system into a contingency state that it was not designed for. So the PTDFs are not as valid. But I think you can make certain justifications on, okay, those measurements I'll still retain. So if I had 28 lines and I lose one, I have 27. As long as I can know that some line has gone out, then the approach will largely work. But if I am unable to detect that topology change, then it will screw up all the results. Yeah.
Sorry, I forgot my question is specific. So are there any like cyber-physical mitigation methods that would work with your detection scheme automatically? And if not, what types of actions would an operator have to take to mitigate that before something bad happened?
Yeah, so that's always a very challenging question, because system operators are extremely risk averse. So something that could be done possibly, for instance, is the moment you flag that time where you see that the error has grown, you could decide to make some corrective action, like trip off a line or just put a hard stop on the ramp that's happening on the DC line. But operators, because of either equipment limitations or just general risk-averse practices, may not want to do something like that. So realistically, I don't know what operators would choose to do in cases like that. You can always have sort of a bypass connection or like an e-stop of sorts that gives the control center, the system control center, some measure of control over the line. And some e-stop like that, so emergency stop, could be initiated in that instance. But again, operators are generally risk averse to having such drastic measures taken from so remote a location. Because
probably some out-of-band communication call with the person that's sitting in the other building and saying, we don't want this to be 2,000, we want it to be 4,000.
Exactly, and turns out that this telecommunication link that I'm saying here is sort of a hopeful future thing. Right now, it's actually someone picking up the phone and telling, hey, can you jack it up to like 1,500 megawatts? And the person on the other end just saying, oh yeah, I know his voice, that's Bob, he's calling me to tell me to ramp up this power order.
So more authentication than RN.
Yeah.
Protocol.
Yeah, so like, that's why the
if you
heuristics
get
is
a deep
important.
fake system to fake someone's voice,
Yes.
spoofing messages is
Exactly.
totally doable.
Yeah.
We probably need to think. What would the goal of someone attacking this be? Like, would it be to destroy lines or to steal electricity or?
Could be, actually, that's a great question. It could be many things. It could be to cause a system disturbance. So you could have voltage sags. So if you inject a whole lot of power into some place, you can disturb the voltage profile in that area. So you might have sections that start tripping off because of under voltage or over voltage conditions. The other thing that could be a potential problem is people might be able to use that to their advantage in the electricity market. So they might hold financial positions in the electricity market, and this sort of helps game it towards a point where they stand to gain profits. So that's actually something that has been looked into, like people injecting false data into state estimation so that they can make money in the arbitrage by selling, buying cheap and selling high.
If you get caught, you are being caught.
Right. So like if you, for instance, if you held some financial instruments if you held, the stock equivalent of like an electricity market LMP in this region, and then you restrict the line flow on this side, the LMPs in this area are going to shoot up, right?
Mm-hmm.
So if you had a time where you have your LMP, so you bought energy cheap and then you are selling it high, then you stand to make a lot of money here. Any other questions? This is going to be my whole presentation, so if you have any feedback, please feel free to let me know. Okay, well, thanks all.
Thanks, Ken.